So we're going to take a bit of a more detailed look at the Modbus driver that we loaded. So right click, views the AX property sheet, and we can tell that's where we are by looking at the address bar at the top. We're in the AX property sheet view. So the enable property, fairly obviously it enables and disables the driver. Fault cause may give you an indication of what a problem is if the driver should ever go into fault. You've got a health section that will tell you the last fault cause. So it could be the port's disconnected or whatever the reason is, you'll get a detailed message about what's going on. There's this monitor section. So every Modbus device we have in the driver is automatically pinged in the background. Now, a lot of these concepts don't just apply to Modbus, it will apply to any driver that you add into Niagara 4, because a lot of these concepts are very much the same. But the device within a network will get pinged every so often, by default every 5 minutes. And the ping is designed just as a check to say, are you still there? And what you might see happening, so I'm just going to do a Control and T for a new tab, is that devices in the network might go different colours. So the white colour we see there is a healthy status. That's what we're looking to see all the time. But you may see different colours creeping in, like a yellow or an orange status for fault or down. So if we were to go and unplug this device at the other end, Niagara would ping it within 5 minutes. Then we would expect that device to turn orange to indicate there's a problem. Anything that you see that is orange will require you to go and fix the problem, either in a Niagara station because of config setup, or physically in the real world because it's powered off or not plugged in, whatever's going on. But this ping will happen every 5 minutes, and if a device does go down, then an alarm will be generated, which will go to its default alarm class. We're going to take a look at alarms in more detail later, but it will generate a comms failure message, which will go to the default alarm class as a catch-all. You can change that to whatever you like later. Then we've got these two sections, poll scheduler and tuning policy. We will look at these in much more detail during this video, but the poll scheduler controls how frequently a point is being polled. We've got these fast, normal and slow rates. But again, we'll go through that in a lot of detail shortly. And then you've got what we call a tuning policy. And the tuning policy is in relation to writable points and how they behave within the station. And again, I'm going to go through that in more detail later on in this video. Okay, so response timeout is 501 milliseconds here. And what that means is that when a request is made to the Modbus network to go and get a value, we expect a response back within half a second. If we don't get a response to the query or the request, the message will just get timed out and it will move on to the next one. In a poll scheduler, we can see that the average poll is 12.5 milliseconds, so it's really fast. But that's a timeout. Once we ask the question, I'm not going to sit there forever waiting for an answer. If you don't reply within a fixed amount of time, we're going to move on to the next thing in the queue. You've got some settings about the float byte order and the long byte order. So it's this concept of when we request a larger value, so a 32-bit register or maybe a 64-bit register from a device, when we get the answer back, do we need to swap the bytes around? So the default is most significant bit on the left, least significant bit on the right, 3210. Or do we need to swap those bytes around to reorganize the number that's received? It will be more often than not a bit of trial and error, reading the documentation and understanding what you're going to get back, and then maybe playing around with the settings to get the right values because every manufacturer likes to do it in a different way. You've got some options about using preset multiple registers and force multiple coils. That's fairly non-standard setup. Never seen those used in normal setups. It's a specific application to go and change those. Maximum fails until a device is down. So how many requests are we going to make from a device and not get data back, related back to our ping monitor before we decide it's not there. There's a socket option timeout of 1 minute. So if there's nothing going on for a minute, the socket will time out. The target IP address of the device that we're pulling data from, the Modbus port, and the socket status there is showing closed. If I now go into the device, go into the point folder, those points will start to pull and that socket status will go opened. Normally it should be open because it's pulling all the time. And we're now going to take a look at the pull scheduler and the tuning policy in a bit more detail. Okay, so we've got the pull scheduler. And Modbus is purely a polling based driver in the master, in this case Niagara 4, has to continually pull the network and get some data back. So in my second tab, I'm just going to go and look at one of the Modbus points, this boiler flow temperature. And the points have this pull frequency. Normal is the default option. So if I go to the blue square in the top right corner of the point manager, and I just add the pull frequency as an option, it won't be by default, then you can see how the points are all pulling. So they're all set to the normal rate. So back in the driver tab, the normal rate is set to 5 seconds by default, but you've also got the fast rate at 1 second and the slow rate at 30 seconds. So I'm just going to I could increase the normal rate, or I could go across and I could select these points and go edit, change the pull rate to fast, and then press OK. And then we'll see that these points start to update much more frequently because they've just been pulled every second as opposed to every 5 seconds. When you've got different types of networks, you have to be very careful about how you configure your polling. So we're going over IP, and it's very, very fast. So we're seeing the average pull is 12 milliseconds. When you're using RS485 networks, there's a lot of things to consider. One, the overall length of a network. Could be up to 1 kilometre potentially. The number of slave devices on that network. So Modbus allows for 32 devices, but the master would be classed as a device, so potentially 31 slaves. But it's not recommended to really fill a network. You'd want to leave some capacity spare. And then you've got to consider the baud rate of that network. So is it 9600, 19200, 38400 bits per second? The longer your network physically in length and the more devices you have, the slower that baud rate will probably be. If your devices are all local on a short, less than 20 meters network, you could increase that baud rate and go faster. But that bandwidth that's available will determine this average pull time, which will then lead into this busy time. So the busy time is 0%. It's not busy at all. That busy time can go up to 100% or even over 100%. So if we think of the comms line as like a drain pipe, the drain pipe has a physical capacity. So let's keep it simple. 100 litres of water a second, equivalent to 100%. And that's okay. But if we start to try and put more water down the drain pipe than it can handle, the drain pipe will fill up and then the messages will start to overflow over the top. And the physical comms line is very similar in this concept, that if we start hitting the messages too hard, then we're going to fill the line with comms. It gets busy, but we start trying to put more and more messages in, it's not going to be able to handle all of those comms. So if you start to see a busy time above 70%, 80%, we want to start to potentially make a change to what's going on. And the reason for that is that if we're running at 80% capacity with everything online, that's not too bad, it's okay. But should a device go offline, then we'll still be polling the device. We'll be waiting half a second for a response, and it's never going to respond because it's not there. And that's going to have an impact on our average poll time and then our busy time. And it'll end up being like a snowball effect that things will just start to grind to a halt and not work very well. You'll see points going into fault and out of fault, and it's just not working very efficiently. So understanding the points that we're polling and how frequently we need to poll them is really important. So if it's an energy total that we're only logging once every 15 minutes, why do we need to poll it every 5 seconds? You don't really. If it's a room temperature, the temperature in a room will not change that quickly. It'll take some time to change. So again, why do we need to poll a room temperature every 5 seconds? We may want to change that point to be on a slower poll rate. But then if it's a supply temperature in a pipe or a ductwork, they will change very quickly, and you may need to poll them more aggressively. So picking and choosing which points are on a fast rate or a slow rate or a normal rate becomes quite important on a larger, busier network. Okay, so you've got the total number of polls, 3,190 over 47 seconds. And we've got what's called DIBS polls, fast polls, normal polls, and slow polls. We can right click on the poll scheduler, go to views, and go to the guide help and pull up the helper. It will explain in detail all of these settings. That has not loaded for me because my load help button's down at the bottom. And again, lots of statistics about what's going on. But if you're seeing a high busy time, you want to start making some changes to how frequently things are polled. And I'm going to talk about polling a bit more now. I'm going to explain how Niagara works in terms of polling. So right now, because I've got the window open, these points have been put into active subscription, and we can see that they're being polled and they're changing value. But what I'm going to do is I'm going to close down the tab and I'm going to come away. And then after a period of time, we're going to see the socket status will change from opened to closed. Now that may take several seconds to happen. I've not got an option to force disconnect it. I could disable my network and re-enable it to force this closed status. Now, it's going to remain closed until I go and force the point back into subscription. And based on how my station is configured at the minute, which is very, very basic and not really functional, as soon as I go and expand the device out, the socket status has gone opened because it's starting to pull the device and it's starting to pull these points underneath. But again, as soon as I go away and stop doing that, the socket will eventually close. So in this situation, things are not continually pulled all the time based on the normal rate of 5 seconds. They'll just turn off. That does start to change, however. So as soon as we add a history extension to a point, or add an alarm extension to a point, or we link mark a point to a wire sheet, or a point is added to a graphic, all of those situations would potentially start the point to being pulled continually. So certainly for histories, alarms and link marking, as soon as that happens, that point is put into a continual polling cycle. And then that will, again, start to have an impact on this busy time of how busy the controller or the station is polling. And we've got to appreciate there is a difference between where you're running your station. So right now I'm running my station on a laptop with a very capable processor. And what's working fine here may not be exactly the same when I commission this to a controller. So the JACE 8000 was released in 2016, and it's getting tired in terms of hardware today, because it's 8 years old at this point. So we'd expect the busy time to be higher in the JACE 8000 than the laptop, and then equally if we put the station into a JACE 9000 or portability controllers like our IoT controller, that busy time may significantly change based on the hardware that's running, because it's purely down to the processing power. So if we compared a Modbus network in a JACE 8000 against our Intel IoT controller, our IoT controller busy time is going to be very low because it's a very, very fast processor, whereas in the JACE 8000 it would be high because it's just a slower type of processor. Okay, so link marking, histories and alarms, we do want to really start to think about this polling rate. So if we're just interested in histories and we're only logging the history once every 5 minutes, is there any mileage in polling the point every 5 seconds? Probably not. Maybe once a minute would be okay. But if we're using that value for logic processing or graphics, we may want the point to poll more frequently, so the screen is updating more often. You've got to get the balance right, and it'll be a bit of trial and error based on the busy time. Okay, so we're just going to take a look at writable points in the system. So I'm just going to go into my plant room, and I've got my boiler enable output point here, these 5 writable points. I'm just going to double click on one. And there's a tuning policy option, which is set to a default policy right now. And there's no other option than a default tuning policy. So again, it's understanding how writable points behave from a Niagara station over a communications protocol like Modbus, but it's not just about Modbus, it could be any comms protocol, BACnet, KNX, whatever you like, about how things behave. So if we imagine that we have a time schedule that comes on at 9, goes off at 5, and it links into this boiler point or pump point, whatever it is. So at 9 o'clock in the morning, the schedule will become active or true. At 5 o'clock at night, it'll go off. So 8:59, it's off. 9 o'clock, it goes from a 0 to a 1, writes to the Modbus point and turns it on. 5 minutes later in the real world, an engineer comes along and turns the panel off where this I/O module is. It power cycles, he opens a door, and then he turns the power back on. The I/O module will more than likely have a default state, a fail-safe position, which will be off for the outputs. And then the I/O module is going to sit there waiting for Niagara to tell it what to do. But by default, the writable data is on change of value only. And that means it will be waiting until 5 o'clock for the next command of off to do something. So we need to be able to change the setup in a way that Niagara will more frequently tell command points what to do, just in case the first one didn't get there, or there's been a problem, it's been power cycled, or whatever. So in the network level, there's a section called the tuning policies. And again, you can right click on this and go to views and guide help and get some detailed information. But there's one there right now called the default policy. It's got several settings in there. It's got a minimum write time, a maximum write time, write on start, write on up, write on enabled, and a stale time. So I'm going to go through each of those and explain what they do. So the minimum write time is like a throttle. So if we imagine we had 10 PID loops on the wire sheet that were constantly changing value from 1 to 1.1, 1.2, 1.3, 4, 5, and so on. Every time the output of that PID loop changes and it's linked to an analog output on an I/O module, that will initiate a write command. So every 0.1 of a degree change, well, 0.1 of a percent change in this case, it will create a write. And if that PID loop's going crazy, very quickly up and down with values, it'll be creating spam down the comms line and creating a lot of unnecessary writes. So by setting a minimum write time of 30 seconds, that would allow us to create what we call a throttle, and it will only allow one command every 30 seconds. The maximum write time we can think of as a rewrite timer. So if I set this to 1 minute, then the schedule changes at 9 AM from a 0 to a 1, and then every 1 minute afterwards, the command will get resent to the target point regardless of whether it's changed or not. Like I said, you're kind of really hoping that the command point got there. There's a very big assumption that it did, but by setting up a rewrite timer with the maximum write time, we can introduce a background rewrite of the value. So write on start is write on station start. Write on up is if a device goes from down to up, it'll resend the commands. And write on enabled is if we disable a device and then re-enable it, any writable points will be processed live. Stale time relates to how long we're going to wait before we class a point as being stale. So this relates back to our poll scheduler. So if we're polling every 5 seconds, we could set the stale time to 1 minute. The point should have been pulled 12 times within a minute, but if it didn't get pulled for any reason, because it's really busy, then the point could be marked as being stale, which means it would visibly turn grey, and the user would then get an indication that this point is not being processed for whatever reason. Now, the default policy is always here, and I don't particularly want to change it, so I'm just going to go refresh and no. And then what I'm going to do is I'm going to right click on the default policy, and I'm going to go duplicate, and I'm going to create a second a second tuning policy called output policy. Now, you can have as many tuning policies as you like, because you may have different applications that require different setups. So this one I'm going to call outputs. Minimum write time of 30 seconds, maximum write time of 30 seconds. So that means it will only allow a value change once every 30 seconds. Maximum write time will rewrite the command every 30 seconds. And I'm going to set a stale time of 2 minutes. And I'm going to go save. I'm going to come to my plant room point folder. And then I'm going to select these 5 points, the outputs in this case, and go edit. And then the tuning policy, I'm going to configure with my new tuning policy. So like I said, you may want just a tuning policy that's got a minimum write time, or a tuning policy that's just got a maximum write time, or a tuning policy that's just got a stale time within it. So we could create another one here, right click, duplicate, stale. So I'm going to set these to 0. Back to the way they were, and then I'm going to leave that at 2 minutes. And then when I come back to my plant room, these temperatures here, I could go and edit them. And again, they're not writable points, but the stale time will apply to them. So if they don't get processed with a new updated value in 2 minutes, they would turn grey because they've not been processed by the poller. Okay, so lots of extra configuration that you can do on any network. It's not just about Modbus. And knowing some of these things is important because it will make or break the system. We see it all the time on technical support where busy times are sat there at 100% and the system's just operating really poorly. Okay, the last thing I'm going to look at is my Modbus device. So I'm just going to go into its property sheet. And Modbus is a very clever protocol. So right now I've got a number of points in my point container. There are 11 of those points. And it can configure it individually. And what that's forcing the setup to do right now is to go and create 11 individual messages to the network with 11 individual replies. So it's kind of like putting 11 cars onto the road rather than one coach or a couple of minibuses. Now, when we've got lots of devices and lots of points, we could potentially be putting lots of cars onto the road, which will create some congestion. And like I said, Modbus is a very clever protocol because it was created at a time when you had to be really efficient with memory allocation and how you requested the data. So where I've got consecutive points, and by that I mean like these three here, because they're consecutive Modbus addresses, 119 to 121. Rather than going and asking for three separate questions with three separate answers, the Modbus protocol would allow me to ask a bigger question. So I could go and say I want register 119 to 121 by asking a single question. So rather than putting my three cars onto the road, I'm putting the minibus onto the road, and that's going to go and get the same information as the three cars or achieve the same result. So the Modbus device has this device poll config table, and if I right click on that and go to actions and learn the optimum device poll config, and I'm just going to go with replace existing entries, what it will do is it will look at my Modbus registers and it will look for any sequential registers like these ones. And again, rather than asking those individual questions, it will say, well, actually, I can start with this register here. I can pull three consecutive registers in that group and give you one answer as opposed to three separate answers. This can have a major impact on comms performance. Again, this concept of the busy time in the poll scheduler. So you may want to, on a busier network, also look at how to set this device poll config option up to be more efficient with how the messages are being put onto the comms line. You do have to be careful though, because not every Modbus device will like being polled in this way of asking for multiple registers in one go. And it might not like you asking for a large amount of them in one go. There could be some trial and error of setting this up to work how you want it to work. Okay, so just another feature that's there in Niagara 4 that can improve comms efficiencies.